Morty. We've got to turn the project in early.
Hey, Nicole, how are you doing? We've got 201, we've got 320, we've got 474. We got so much on the plate right here. But what questions do you have? Because I've got 4 things lined up. Woo! We got TV ads. We got a bunch of stuff. We might just hop in here to TV ads. But Nicole, if you have a question, put it in the chat. We're going to wake up Mubot. BSB2, you got it. Let's do that. Your question is first because you are here. We've got other things lined up. Thank you for being here. Hashtag show up. I'm going to put some music as I bump my board. I'm probably going to knock out the wires. Is my Philips Hue lights working? No, my Philips lights are broken. I've been trying to fix my 1B2, or wait, 1B2, got it. Been trying to fix my Philips Hue lights. Thank you so much, Nicole. I am married. Got married on Saturday. It's the Married on Saturday song. But that's, we got some good stuff lined up. Thank you so much. So many nice congratulations from everybody. Just really nice time. Logistic regression, what? Q1B2. So we have to do B. So let's just put this as B. And so let's go right, Okay, so this is going to be B1 and B2. Perfect time right here. We'll put the timestamp in. 2, 35, 36. Let's do this. Here we go. Okay, so let's take a look. Yo, Carter, good to see you here. Throw out some Mubot points. We're doing some logistic regression or linear. We'll find out. Let's explore if homeowner is a good predictor of what. We got to know what it's predicting. We are trying to predict last amount from homeowner. And so we're going to predict last amount from homeowner right here. Yeah, I think we can put it on here. I think we did it yesterday, but we'll check that out. Is that the, or did we do that earlier? We did it earlier. We did it earlier today, but we can check that out. At the 15-minute mark on the morning video, we did it today. Oh, check that out, Carter. We'll try to swing back around and do it more, but that's the time series linear models from earlier today. Check out the 15-minute mark from the morning office hours. We could swing back. Oh, no worries. Yeah, tell me if you have any questions. And so that way, we spent a good 19 minutes on this morning. Yeah, good stuff right there. And Carter, thank you so much. 100 points. Thank you for asking. Taking the timestamps down as we're doing the work right here. Allows me to take some like better notes on what we do and then post in the video later for you to check out. So we're predicting last amount, which is the last amount somebody donated right here. Let's load in the data sets. I've got a whole bunch of data sets right here. We're just going to clear out all that. We're going to clear out all these plots right here. Carter, make it happen. You got this. Ask all the questions. Let me know if you're stuck and we can swing back around. You're here, so you get the priority. We've got some questions listed, so we're going to try to get through as many as we can. But if you're here, you always get the priority on what to ask. And then we list questions that people ask, and we try to get to as many as we can. So we are using homeowner. So you build a model. I could have just looked at the question. Predicting last amount using the variables. Now, here's the thing. We're using the donor data set. Now, a lot of people are wondering, when do I use logistic? When do I use regression? Which is a topic we covered earlier today. How do we know when to use logistic or when we use regression? So here is, this code won't work. Here is regression. This is regression, like linear regression. When do we use linear regression? These are things you need to know. When do we use linear regression? The answer is on the screen on one of the lines. When do we use linear regression? When do we use logistic regression? There's logistic. And when do we use linear regression? When do we use logistic regression? So what's the big, like, okay, logistic is for when this. So make sure you know this. Notes on the screen right there. Big difference between the two. Logistics are probability, categorical Y, because the probability of somebody being male right here is being predicted. So a good question for these assignments then is, am I doing logistic or am I doing, because that's going to change the type of model we're fitting, whether it be GLM with family binomial or just our classic Y tilde X, data equals. So linear is for, well, kind of. Good answers. Nicole, right there, good answer. The only thing that matters about logistic versus linear is the what variable. The only thing that matters about logistic versus linear is the what variable. So when you're choosing between logistic and linear, it's really the what that matters. Like the Y variable, exactly, Nicole, and great right there. I tried to point out some hints as we talk through this. The Y variable. You can include categorical X's right here and then you're looking at indicator variables. Does that make sense? If the X is categorical, you're doing indicator variables. If the Y is categorical, you're doing logistic. Does that make sense? Categorical X's creates indicators, and you can see that here in my model where we have a quantitative Y, weight, which is right behind me right here, and then we have a categorical X, which is indicators, creating two separate lines. So categorical X's create indicators, great note right there. Categorical Y's switches the type of regression to what we call logistic, where we're predicting the probability. Now, what you could also do is you can do indicators here, like handedness, and you will get 3 separate logistic models. So now this is a categorical Y with a quantitative X and a categorical X. And you can even do interactions, which would change and make them not parallel. So we have the same sort of concepts back here where we have linear with lines, and then we can do an interaction and they're not parallel. And the interaction is so weak that you really didn't see any change right there. Desired weight. Is it capitalized? It is. There we go. Now we see some little stronger interaction versus the no interaction model. You bet. Computer, you got. We'll probably do that one next. Thank you, Thorell. Got it on the list, and we'll do it next. Let me move it up. So very important right here. It is next on the list, Thorell. Thank you for asking. And so with this, the choice between linear and logistic is very important. And we see right here we are predicting last amount. So LM or GLM for last amount? What do you think? LM or GLM? Which one should we do, Nicole? Should we do LM? It says it's num, which means numeric. Should we do LM or GLM? Which one should we, what function should we run? Should we do, because we're going to predict last, boom, Nicole, another 100 points, because that's numeric, that's quantitative. So factors are categorical, integers and numeric are quantitative. So that kind of did the decision for us. And if you're really wondering, you could always go into here and go to the Homework 10 data frame and take a look at it. It doesn't hurt to look at data. And you could go to last amount and see its numbers. That's a graphics error. You can see its numbers, and we can know we are doing linear regression right here. So we are going to store into a model, a linear model. That's M for model, linear model created, Y tilde, there's the Y variable, and it says end their interaction right here. So we need to use these variables. We're going to remove off this, include their interaction, and then we need to go to Y tilde X, comma data equals. My brain broke. Homework 10. It worked. So there it is, and now we can go and view this. Let's decrease fonts so we can get it nice and neat right here. And we fit our model. And now we're going to summarize it. Summary of M. 21 warnings. Oh, why is it giving me warnings? And let's visualize it. We have an interaction. There it is. Y till, yep, I got right there. Can you also do... yeah, you could. Yeah. If you notice, we'll get the same model. 100 points right there. Great answer, Nicole. You are correct. You could do that. What Nicole's written right there is they've written the terms. There it is. And now they're including the interaction. Just to confirm, if you take a look at this right here, recent home owner, where is it? Oh, not that, it's this. There we go. And if I visualize this, notice how it's the same exact picture. If you go between the pictures, there's no difference right here. So these are the same things confirming. What actually, this is a good topic, Nicole. The reason this works, if I don't do this, the colon, but I do the star, so I'll tell you the answer to this. It works because it assumes you want to keep model hierarchy. Model hierarchy is when you include the lower order terms. So by using the star, you include both the interaction and the lower order terms. Model hierarchy says if we have the interaction, to have model hierarchy, we have to have the lower order terms. The interaction being here and the lower order terms that build the interaction being here. Thus, by having the interaction, we have model hierarchy by having the lower order terms. If you don't want to keep model hierarchy, you can always use the colon, and that'll just give you the interaction. Now we have kind of a different way of doing it. I wouldn't suggest this, but now we have just an interaction term here, and it's built a little bit differently than we usually see it. Hey, Kayla, great to see you here. Doing great. I've talked to all the Kaylas today. Well, no, I have more Kaylas. We got so many. I love it. It's so interesting. I think I have like 4 or 5 Kaylas I teach right now. I never would have thought. It's interesting. Like, I think Kaylas have even told me that their names are not as common, but had a lot of great talks today, and Milton Scholar Kayla's doing great. Other Kayla's doing great. We're on question 1B right now, talking it over. showing the work. Me about saying hey to everybody right there. So what do you notice about this? Let's see. Build the model. Run this. Again, we're good. We're good. Is the strength of the relationship between last amount and recent average amount stronger for homeowners or non-homeowners? How can you tell? So what line is stronger, the no or the yes line? Pretty easy to tell right here. Which line is stronger, the no or the yes line? The no or the yes line, which just taking a look visually. You can just look at it visually right there. The no line, because it's steeper. Now, think about this, though. If you think about this, the no line has the slope of, can you tell me the slope of that black line right there? Can you tell me the exact value of the slope of that line? You've got a lot of great practice. You're like, oh, the slope of that line is this. Tell me the exact slope. Thank Dwight. Dwight. I'm going to be sending like some stuff. We're doing a lot of physical photos, so I'll send you some physical photos. I'm sending them to, I'm going to put some in my office. So students, if you want to see it, we're going to have physical photos in my office. Dwight, thank you so much. Crazy busy weekend. We're going to send out some physical photos too, especially so students, if you want, swing by my office. We're doing a lot of physical photos because we're not posting to Facebook and stuff, but I'll send you some physical photos because we're not putting it all over social media. I don't know. But Dwight, thank you so much. Crazy busy weekend. Oh my gosh, it was so busy. I was telling someone, oh, that's why I said, yeah, it's the reference. Thank you, Dwight. Thank you. It's always good to see Dwight here. He's got his wrench. I'm excited for you got it, Nicole. Great job, Nicole. Dwight, it was like Friday to Sunday night was just like, there was barely any time. We came back from our wedding. Oh, it was really good. Chelsea said she wanted to look like a princess, and she did. Like, everyone was very, I don't know. She doesn't usually talk about wanting to look like a princess, but I think, it's her big day, and she's like, I just want to look like Disney princess or something. She didn't say Disney, but she did. Yeah, she really did. And just like, I was like saying to her, like, when we were getting married, I was like, you look beautiful. Like, we're the pastor's saying stuff, and I'm half zoning out because I'm just looking at her, looking at her eyes, and we're just staring at each other. And I'm just like, okay, let's swing by my office. I'll have pictures, and then I'll show it because we're not blasting it all over social media, kind of keeping a little bit, but I'll have physical pictures. Alyssa, good to see you here. And so, yeah, just like I said to her, I think I said, you look beautiful. And she says, what? And I was like, you look beautiful. And she's like, what? I was like, you look beautiful. She's like, oh, thank you. I was like, I love you. And she's like, I love you too. Yeah. So, she cried. I didn't cry. Her mom cried. She cried. I didn't cry. I was just thinking, don't cry. If I cry, because she was crying, and she was sniffling and crying. I think I tell that story. I would have cried. Aw, it was really special. It was really nice. Like it was beautiful. It was such a great time. And and the funniest thing, I'll tell the funny story real quick. It is the black line. We've basically done this question. Nicole, you are right. The coefficient of the black line is this, and then the slope of the red line is this much less. This is the difference between their slope because it's the interaction. Yeah, I'd say it's the best day of my life. I'd definitely say that. I think the best. Nothing went wrong on the day. Nothing went wrong. We had a great time. Nothing went wrong. Like everything went right. I guess if anything went wrong, which I don't even think is wrong, when we went to Texas A&M to take pictures at the Gardens, there was a parking lot that was like a 5-8 minute walk away. Like, like you just kind of walk across, nice little walk. So homeowner, yes, would influence the intercept, right? Yes, it's going to influence the intercept and the slope. It's less sloped and higher intercept. This influences the intercept. It's definitely. If we write some models of lines while we talk through this, is the difference statistically significant? Yep, it is. It's statistically significant. And I think that does it for this question. Is it? Well, it doesn't ask us to write it. Yeah, the strength for no is stronger. It's steeper, and it is statistically significant. But yeah, when we went to the Gardens, I had to park like a 20-minute walk away, like over half a mile away. So I was carrying in the party favors, and I was just like, I was like, I am going to be a ball of sweat by the time I get there. And I was really worried that the pictures would come out, but it just turned into one of those adventure things. Like the photographer showed up. Huge shout outs to our photographer. She did such an amazing job. So a little bit, it was a little breezy that day, which was nice. So it was windy. It was 75, 80 degrees. So we're lucky it wasn't like burning hot. If it was burning hot, I would have walked over and just been like, yeah, just like horrible looking. But it turned out nice, and it was a really nice, like we were there in the evening around 6:30. So it was, starting to cool down, but really great stuff and really nice day and just amazing. And we got to see so much family and just very nice time. So that's the way weddings should be, just a nice, happy time. We're gonna have a big celebration when we get back to Knoxville. So swing by my office too, check out some photos. I was sweating my pictures, but I didn't, so my face. Nice. Aw, that's awesome, Kayla. And congratulations, Kayla, right there. Oh, I'm just so happy. It's, you got to share those moments with the people you love and your family. And it was just so nice that my parents were able to come down here to Texas. I'm married in Texas, got a Texas wedding license, say born in New York, raised in North Carolina, from Tennessee, I guess. Am I a Tennessean at heart? Well, married in Texas. I got to do something in California. I got to go across the whole United States, or I got to circle up to like the North Dakotas. I don't know. What's there to do in California? Anything? Bueller? Yeah, I know. It was a big thing. It's a long way. We got printer computer problem. The printer problem coming up here. The printer problem. Yeah. Here. That your print? Yeah. You're from CA? What's there to do with Darrell and CA? What's there to do in California? What's the best thing? Should I do a guest lecture at Berkeley? It's Berkeley in California. Can I go over to Berkeley? I'm not going to go work there. UT, you're fine. We're getting this loaded up here. Question chapter 15. Computer printer. I can't find the computer printer problem I'm looking for right now. We got the startup company with the new computer printer. Startup company. We'll call it startup company. Startup company. Printer problem. Let's go check it out right here. 18 minutes in, having a little fun, relaxing, talking about weddings and good stuff. Let's check out the computer printer problem. Put those questions in the chat. We got a lot more time today. Here we go. Okay. Mount Whitney is a cool place to go to, near Death Valley. Ooh, that sounds super cool. In a group me for one of my classes, someone asked about stats. Aw, that's so nice. I really appreciate it. Yeah, we're just here to have some fun, relax, and have a good time. I love working stats. And Kayla, you are a rock star at this stuff right here. We're just throwing out another 100 points because guess what? We know the first thing we do whenever we get to a problem. What is the first thing we do whenever we get to a problem? We draw a neural net. That's what we do. 474, 475 neural nets. We don't draw a neural net. What are we doing with the first thing we get to a problem? You get to a problem. Talk about training and holdout. Nope. You get to a problem, you do what? This is the basis for acing all the assignments and all the test questions. You always have to do this when you get to one of these problems. The very first thing you do, say, okay, you're probably someone saying it, Brian, I'm ready. Notation right there, 100 points. So notation's the key to solving any one of these problems. We see the alpha level right there that they're using. We see that they have 179 adults out of the 410 selected adults. The company's goal is to get over 35%. That's their goal. Be one with Leo. Oh my God, we should tell Leo about that. He might be here somewhere. He might be lurking. That's awesome, Terrell. Terrell is worth some 500. Okay, so can anyone name any of these values we marked? So what are these values we mentioned right here? What are these values? What are any of them? Just any of them. It says a startup company is trying to market a new printer. It decides to gamble by running ads on the Super Bowl. The company hopes that they can get recognition. They want over 35% recognition from people. They talked to 410 people. 179 know about the company from the ads, probably, and they want to use a 0.05 alpha. That tells us what that last value is. So when you look at this, identify all the values right here. Great job, Kayla. Another 100 points. You know what, Kayla? That's for some 500. Kayla practicing the 201 knowledge while in 320. We love it. Practicing 320 while in 201. That helped out too. That's X. That's N. And that's P naught. That is what they're testing against. That's the hypothesized or tested value that they're trying to make statements about, that they're trying to get more than 35%. That's going to be super important here in a moment. This is the alpha level, which is their rejection criteria, at which point they will reject the null if they have a p-value less than alpha. So we've identified all key components that basically comprise this problem. You could like take this problem apart and turn it into Brian wants to see if over 35% of his students are from out of state. He talks to 410, 179 of them were from out of state. Is this evidence that more than 35% are out of state? If you notice, as Rock would say, it doesn't matter. The context of the problem doesn't matter here. I mean, it does, but it doesn't. It's just to see if you know how to solve statistical tests. So when we do this, the very first step into doing a statistical test is to write out the null and alternative. You'll notice we're doing this without looking at the problem to make sure we understand and know how to do the steps, because it's just going to ask the answers to these questions that we're about to do right here. Now, what does the null always have? You just have to put one thing in the chat, but you should know this by heart now. The null always has the what. The null, and I might even make a video about how to write the null and alternative every time for statistical tests. The null always has the what. The null always has the what sign. Like you write your null hypothesis states. That's what this says. Null states, alternative states. So that just says the null says this, the alternative says this. It's like, you're just saying, it's like a box. You're like, here's my null, and they have another box. Here's my alternative. It's just saying the null states this, the alternative states this. The null always has the what, though. Because we're always doing a starting initial belief. Oh. When you see a Kaylee, you'll be like, oh, of course. Carter, good to hear from you, and tell us if you have any questions. We could jump to that next if you want. Well, the null makes a statement about the truth, and it says that we know what the truth is. The null gives our current belief. So we're going to say we know what something is. We're going to say it's equal to something. And the alternative will try to convince you elsewise an alternative to what you currently believe. Now, if you look, in the question, it'll give the sign for the alternative. The question, the researcher's question, is always, it's like, oh my, of course, the equal sign. The null has the equal sign. The null, you're like, what's that? Oh, I didn't, yeah, that's what you're asking. Of course, I knew that. The null has the equal sign. The alternative sign is decided by the wording of the question, not the data. Not the data. So we can eliminate this down to this. We've got a few components done right here. Now, a good thing to note from our notation, so for the model research, 4C, oh wait, you can use the 4C. You can use the linear model, I think, because it wants you to create different models, right? So if you're looking at question 4, I think you can use a linear model there. Good work, Carter. I think you can use it as one of your models because you're just creating, I think, 3 models. So you could use the linear model, I do believe. If you look, this is the hypothesized value. And if you notice that your hypothesized value from the notation is P naught, well then you will just put here P. So I want you to notice this format right here. Now, this is not what the question states. But what if our, for another type of question, what if our hypothesized value was mu naught? What would go right here? If our hypothesized value was mu naught, best question mark ever, what would go right there if our hypothesized value was mu naught, like some hypothesized true mean, then we'd be saying that the what is equal to the hypothesized value of the true mean that we're hypothesizing is the true mean. So think about the format I just where P equals P naught. And now if you did something equals mu naught, you would state that what? And this is not this question, but we're just seeing how this format works right here. We would say that what equals mu naught. And this will help with just writing nulls. Because if we have something equals mu naught, the something that equals mu naught would just be mu. Does that make sense? The format we are using is not that because we don't have a hypothesized mean. We have a hypothesized proportion, what we believe the proportion to be. And the reason we have a hypothesized proportion is because the data is categorical. We are asking if people know about the printer brand. And the question would be, do you know about the printer? Yes or no? And 30 or 179 of them said they do know about the printer. Since we are hypothesizing a proportion, we're hypothesizing that the truth is equal to it, and we want to see if there's evidence that the truth is greater than it. We currently believe it is 35% until we have evidence to suggest it's greater than. And that's the null and alternative. Now we get to where we actually have to run the test. To run the test, we need to solve for the z-score. And so the second step right here is your z, t, or chi-squared. When you solve for the z, the t, or the chi-squared, it's always standardizing a difference. So the top part of the equation is just the difference between your observed value and the hypothesized. That's just how far the two things are away. Ah, oh, 4B. Oh no, Carter, 500 points. Oh no. Carter, you're asking about 320, right? Carter, I'm so sorry. Carter, it's 320, right? Well, let's do that next here. Oh, 475. That was for still well-earned points. And if we have a difference, we need to standardize that difference. They're doing linear models too, Kayla. They're doing linear models everywhere. 201, 320, 475, maybe 474. You never know. Linear models are very important for all of statistics. So our p hat will be x over n. So let's go solve for the p hat up there. Now I have unearned points. You got them. We're here to have some fun. P hat equals to x over n. So we're just going to take our x over n right here. You are in the and so 179 over 410 and 0.4366. And this is x. We don't need this one anymore. X is this. N is this. And that's p hat now. We'll make p hat lavender. Is that lavender? Sure. There's p hat. And now we need to go back down to here, do p hat. What's p naught? P naught is green color. P naught. How if p naught is 0.35, what is q naught? Who knows what q naught? You can try. Mubot doesn't do it. He only listens to me these days. I'll show you a trick here after this. Stay tuned after this problem. We'll do a quick trick that I made up. You can see a new effect. You can see something pretty cool I've got going. Does anyone know how to find q naught? P naught is 0.35. How do we find q naught? So think that over while I solve this for what q naught is. So p hat. I'm gonna awesome. See you later, Kayla. Kayla's got it. 100 points, Kayla. It's just 1 minus. Those two add up to 1, 0.35, 0.65. So make sure to do that. Okay, so we solve the bottom first, because the bottom's the standard deviation. We're going to keep... Oh, we can't keep that. It's going to go away. .6376. There we go. That's the z-score. Okay, cool. I can finish this one up pretty quick if you want to see the cool trick. It's pretty fun. You'll like it. And so now we go here. And we want to see if it's increased, right? So here's the thing. And Kayla, do you have any guess of the p-value? Because we're all the way. This value right here that we just found is all the way over here. And because we have the greater than alternative, we're solving to the right of it. The sign of the alternative tells us which way we're shading on the curve. And the thing is because we have a z-score that's so large, that is basically none of the curve. Remember, we're shading to the right because this points to the right. And so when you go and put in your z-score, which I'll show it here on the table, and shade above it, well, that z-score is going to be basically no area. That's as small as it gets. The applet can't even tell you a smaller value. So when you look at this, we get to the fourth step right here, which is either reject or fail to reject. So this one right here is going to be reject or fail to reject. And since the p-value is so low, back practically 0, we are going to reject the null. When the p-value is low, we reject the null. So we are rejecting it, and we would say we have evidence for the alternative. So we basically did all the steps to the problem right here. The null has the equal sign. We're testing to see if it's greater than. The test statistic right here was computed to be 3.67, and it's going to be 8. Let me look. 3.68. There we go. The p-value to 3 decimals is, let's put in 0. You better like that. And thus, did they actually have evidence of the alternative? Yes. The company found out that, in truth, it was 43% of people knew about it from their sample, which is evidence that more than 35% know about it. It's not just that 43 is greater than 35, it's that 43 would not be likely given 35 is true. Thus, we do not believe 35 is the truth anymore. We reject 35 and have evidence that the truth. So, yes, because the null is rejected, there's sufficient evidence that more than 35 know it. And there we go, another 100. And let's see some effects right here. Here we go, Ova, to the courtroom. Where you at, Mewbot? There he is. There's Mewbot. Mewbot, you doing all right today, man? You doing all right?
Yes, Brian. I am doing great. Mewbot is excellent.
How are you doing that, Mewbot? How are you talking without me? How are you doing it?
Brian, I can... Nope. Brian, you're not supposed to move when I talk. You stay still there, Brian. Yeah, good. I'm talking now. You stop that.
I gotta get it to a better format here. But yeah, Mewbot can talk and I can talk right now. No, it's totally just...
I am Mewbot. Brian is Brian. He is doing his own thing. Mr. T is over there too. Yes.
Stop moving your mouth, Mewbot, when I talk.
Yes, there we go. Perfect.
Yeah. So working on that. I pay the fool right there. But we got our courtroom set up now. Just trying to make some new... Yeah, so it's... What I do is I can freeze myself here. Well, I didn't hit the freeze button. There we go. And then I can unfreeze. So I've got a button that actually freezes my webcam. So I just freeze my webcam right here. And so there's a button I have on one of my stream decks to do the freeze effect. And then the Mewbot talk is a button right there. I can get him to talk when I want. So I have to hit the freeze. I should make it a multi-button. I should have just done that, and that'd make it easy. Because I'm actually having to click between multi-buttons. But you can do, let's just sort of set it up better, which I'll probably do next time. Because right now I have to click freeze Brian. Then I have to change voice.
Change voice. And I have to make Mewbot talk. So there we go. There's Mewbot talking.
And then I have to like unfreeze and stuff. And I try to like sit like this while Mewbot's talking. What I'd love to do, and this is the last thing I'll say on this, and we'll do some more questions, is I want to make it so like if I could like put it to like a loop. I think there's a way to loop my video. And I might have to section the screen, but I could almost make it to where like I could do something that's more of like a loop and like just scratch my chin or something like, what do you think, Mewbot? And scratch my chin and then have it do like a 1 second loop. So like I'm still moving and then Mewbot's talking. Court day 2, exactly, Troy. I was talking about the magic behind this on how I can like freeze my screen. And that's what I was doing right here yesterday. People might have been able to figure out how the effect is done. I can't hear the loop same way ever again. Yeah. So I don't know. I like playing around with these effects and seeing what I can do. Mr. T is actually transparent. Part of his... Where's Mr. T at? There's Mr. T. He's partially transparent. I just got to give him a spot. His I alpha keyed out some stuff on him. Oh, 4 loops because of 4 loops. Judge Mr. T right there. Let's head back to the main screen. So, oh my gosh. And then I got to make it so Mewbot goes away right here. But Mewbot. So Carter, what were you wondering about? We got time for more. We got way more time right here. We just did the printer problem. We got TV ads. So let's look at some TV ads right there. Having a little bit of fun here on office hours. No, don't cry for 4 loops. Don't cry for me, 4 loops. Something, no. They are working on 4B. 4B for 475. You are here, so let's do it. 4B 475. Let's see. If you are here, we got time for more questions. They are working on my roof today, which is awesome. There we go. Could a remodel be a good one? Oh, yeah. Yeah, use Arima. Use Arima as they bang away on the roofs and the ceiling. Use Arima. Oh, we're doing stretch chisel. I'm going to allude to this a little bit right here. Where's my model I was making earlier? Oh, won't let me undo it. Let's see right here. Let's do a little 4B jumping right into it. Or wait, did you say 4B or 4C? You said 4C, right? Let me close out other chats. 4B. 4B. Okay, wait, here we go. Oh, you're splitting the data. Yeah. Let's split the data. Yeah, we can do this one. We can just flat out do this one. Okay, let's split the data right here on 4B. And there we go. Here we go. 4B splitting data. Okay, with splitting the data right here, we need to take our timestamp first, 3615, and make sure you have your data already to 475. Yeah, well, this one does it differently. We're going to do it differently right here. We got a whole bunch of craziness from 320 right here, but this is a little bit differently because when we're working with time series data, we can't do it the same way as 474. 474 takes the rows Howley, Carter. So 474 takes your holdout sample Howley. How does 474 take the holdout? We had a lot of fun today in class because we were running into problems with the gaps in the data. You can't create gaps in your data, which taking random rows will do. Assignment 11, number 2. Yeah, that's 320, right? Is it 320, Kyle? I think 320, right? But yeah, Kyle, we can definitely do that. Good questions. That's the next one, right? Ooh, Kyle, 100 points getting ahead right there. I like it. So in time series, we can't take it randomly. Number 3 on the homework. Yeah, pretty good questions. Good question. We'll be doing all those here soon. So we are going to take the end of it as a holdout to predict the future. Let's see. I think I've got part of this set up. Let's see if we actually have our time series data. It looks like we do. So here's our TS hotel. We've already turned this into a Tizble. So if you're watching this video, check out other versions or other things we're doing where we have our time series hotel data. We're going to pipe it in autoplot. Don't include this here. That's just to show we have what we want. It's assuming I'm using room nights, but we're going to go right here and turn this into, we don't got to worry about that. We're on B, right? We're just confirming we have this set up. So watch the other videos on how to turn it into a Tizble to make it a time series object. And now we can start working with it. Okay, so when you're looking at this right here, split it into a train. And I usually just call it a holdout or a test. Either one's fine. Use the last 12 months of the data as the holdout data. Now, probably a quick way to do this. I'll bet you a certain quick way. Can you visualize it? Yeah, Therrell, you're asking about that. Definitely. Let me take those notes here on all those between the sections. So I'm going to take notes on everyone's questions. Thank you, Therrell, 100 points. I think the quickest way to do this, since we're asking for the last 12 months, TS hotels, there's the last 12 months. What if we did? So those are the observations. I'm thinking because it's a little bit ridiculous to do this. That's such an easy way to get. Oh wait, could we minus the tail off of it? Let me take everything but the last 12 rows. Wait, let's go here. Let's go here. TS hotels. I should use proper. I'm gonna show a few ways to do this. Oh, just think of ways to do it. Rows, everything but the last 12. Well, 1 through 174. Is that right? There we go. And then TS hotels. Let's go right here and take 175 through 186. That's 12. Okay, we've done it. And let's call this as train. I might do this a little bit better. Let's call this as holdout. That is looking good. That's good right there. It does it. There's probably better ways. There are probably better ways. But you kind of have to know what the last month is to do it this way. Let's do it another way. Okay. So probably the better way is to go here to your train. You can just call another train object. Take your time series data. Make sure it's time series data. And what we should do is we should probably filter it. When you're using the filter option right here, you can do it based on, what is the name of my variable? Month, it is month. Good. That's my time series index, month, less than or equal to. And if you look at the data down here, we need to go into, looks to be going to sort of June or July of 1995. So let's go right here and say less than or equal to 1994. We got to call it a date though. This is a year month. So there's your month. And let's go right here and go 1994. And this is going to take everything at or before. And if you look right here, the train is the same. So that kind of confirms we're doing it the same way. So now for the holdout, it's going to take right here and go holdout greater than or equal to, or not greater than or equal to. We don't want to include the last date. And that confirms. So kind of, does that make sense, Carter, right here? Yeah, it's that, yeah. You can sort into training, whatever you want. Either which way works. There's a bunch of ways to do it. You could take the tail of the data set because you could have just gone here and you notice that the holdout right here, we could have went to tail of, what is it, TS hotels and go to 12. So that confirms the holdout is still the same. And it should be you might want to make sure it didn't lose like its class. And it's still got everything on it, the same as the other. You could go here. And I'm thinking like taking not that. What do you do minus 12? Ooh, that's super cool. Exactly what I thought it would do. That's cool. That's fast. That's what we're looking for. So that says do not take the last 12, everything but like remove that. So if you do a minus on it, it takes out of the series. So that's really, I mean, I know it doesn't use FPP3 format, but still that's way easier. So check this out. I want my train to be everything but the last 12 at the end of it. I want my holdout to be the last 12. So that's way quicker than having to think, yeah, that's super quick. I was like, I wonder if that'll work. Like theoretically, I was like, what is that code going to do? Does it do what I think it does? So that's just like that. And then just try things. Just like, if you know what you should be getting, you know what you want to create, and we know what it should look like. We should know the holdout should be the last 12 months. The train should be the everything but. So we should get 174 and 12 because that adds up to 186. And they should both still be time series. So you might check your class or your object and make sure they're both still TISBLs, and they are. So, hey, Christopher, good to see you here. But yeah. So Carter, keep checking it out. And good questions on question 4B right here. Making your train and your holdout. And as you notice right here, we are doing the 475 methods of taking the holdout, where we're taking like the last 12 months, not random rows like we do in 474, because we don't want to create these gaps in the data. You're welcome, Carter. 100 points. Great work right there and good practice. Good to see you, Christopher, as I said. And let's keep going. More points in the chat. Okay, back to the main screen. Here we go. Let's find out those questions. Oh my gosh. I'm falling asleep, everyone. We got the TBAs. There we go. Kyle was asking about, let me put it over here a little bit. Kyle said BAS 320. I think we're going to do Thorell's question next. They asked it at early office hours, so we'll do it here next. Thorell will do visualization 7 next. BS 220, assignment 11. Number 2. Q2. And then Priya wants Stat 201. Chapter 15 homework. Question 3. And visualization 7. I think that's got it. Okay, cool. Let's do some visualization. So 2C, 2B. 2B? 2B, Kyle? Cool. Okay. I am sorry, everyone. I'm gonna sleep one of these days. One of these days I'm gonna sleep. One of these days. Okay. Let's get some, no worries. My brain is just thinking through it. It's funny, when I first started streaming online, I was a lot smaller on the screen. I look back at my the way I used to do streaming, and I'm small in the corner, but it's funny to see the original stream. I'm so small on this screen. Now I take up a lot more room, and it just works a lot better. It's better. I've made a lot of changes here over the days. A lot of changes. Let's go. Let's go have nap time. We'll go all have nap time. Let's take nap. All pass out. Logistic regression. Logistic regression part 2. Getting it downloaded. I close the page. Here it is. Logistic regression part 2. 2B. I think it was 2B, right? 2B. Oh, we were doing... We'll do this first. Thorell, we'll do it next. Visualization 7 next. I already got slowed up. My brain just skipped a beat as we were talking about 2B right there. We're going to do visualization 7 next. Stay tuned for visualization 7. It does sound like Tron to me too. I like this one. It's getting myself a little hype right here. Okay, let's go check out 2B. Here we go. Grab that timestamp. We were at 45:55. Good to see you here, Alex. And there we go. Time to go. The model assumes one curve fits all. In other words, it assumes the shape of the logistic curve describing how the probability changes with alcohol is the same regardless. As in other words, it doesn't matter. The relationship between P and alcohol may be different based on things like volatile acid. Redo the previous model and include the interaction between the two predictors, examining the summary and the visualized model. So we need to grab, I think I might not have the data frame loaded up for this. Let's clear all this out. Going great, just relaxing, having a good day. Gonna grab a little more food here in a little bit, maybe some chips. Don't tell anyone. Gonna grab some chips. Some snacks. We got so many snacks from the wedding. Just nice, good party food. So we got the wine data. We have some champagne. That's for later, obviously. So we still have some champagne from our wedding. And here we go. Let's see. Okay, so we are predicting a model for the quality of a wine, high or low quality. And it says which one has the higher probability. We need to go back to the model. Fit a model predicting quality from volatile acid and alcohol. No interaction. Okay. Now here's the issue. This is what we have to know immediately. If we are predicting quality of wine, what do you immediately notice about the quality of a wine? Which is like, this changes the way you do everything. Your whole world has been flipped, turned upside down. What is the difference right here with predicting quality of wine? Quality of wine is what, thus, we need to do something different. Everything's changed. Everything's changed. Nothing will ever be the same again. It's a factor, Kyle, great job, which means we are doing logistic. Logistic is for categorical X's. Categorical Y's. See, I even got to practice. Logistic is for categorical Y's when we predict the probability of something, and we'll see that here especially as we make our model. So let's go here to LM, predicting the quality of a wine, and you don't get the autocomplete because it's inside of a data frame. We're going to double-click the variable names to make sure we spell them properly. That is a capital Q. It says no interaction, and now we're going to do data equals ex6 dot wine. There we go. Oh, I said to do it and I didn't do it. GLM comma family equals binomial. I literally was alluding to that. There we go, and that's the error you'll get. Just trying to show you the errors you'll get if you don't do GLM, which is generalized linear model, because this is going to allow us to fit a binomial. It's more general. I know, right there, Kyle. I was just trying to make everyone feel good about themselves. I was just trying to help out. We're all good. There's the fit of the model. Let's visualize it. Now, this model is a what shape? Just one letter in the chat. This model has a what shape to it. I'm going to zoom out here a little bit. We'll add in the X limbs right here, location of the little extras. The model has a what shape to it? The model has a what shape to it? What is the shape of the model? What letter shape is it? The model has a what shape to it? And you can see it more right here. We call this a what shape. So think of the letter by the name of its shape. What letters do those look like? And this is actually a multiple logistic because there's a categorical X, there's volatile acid, which is categorical, which is indicators, and there are quantitative because we have volatile acid, which is how much volatile acid is in the wine. Where, yes, the alcohol right here is going to be, this is volatile acid. That's weird that it does that. Yep. So we have right here the volatile acid for small, medium, large. And then we have here the volatile acid right here, which is interesting how it's doing that. But right here, you'll notice that is an S shape. That's sigmoidal, S-shaped, sigmoidal. And this right here is the quantitative variable, so it makes more sense. I think this one's being a little bit weird. I want to look more how this one's plotting this, because I'm wondering what exactly it's doing. I think it's using 0, 1. Yes, this is not as important because it's turning those into... the indicators are a little bit weird. That's why we're focusing in on this one right here. So these are S-shaped sigmoidal curves predicting the probability of low quality wine. So frankly, Do you want lots of alcohol in your wine? Do you want lots of alcohol in your wine? I know you might be thinking yes, but maybe the answer is yes, maybe it's no. You'd want high quality wine, but two wines that differ in their alcohol by 1% alcohol, if this is percent alcohol, the wine with higher alcohol would have a lower probability of being low quality. Look how the slope goes downward here. So with this, we would say that, yeah, if we're making wines right here, we would want the wine to have a higher content of alcohol because it has a lower probability of being low quality, i.e. higher probability of being high quality. So that is a good thing. But what about if we include an interaction term? And this is what the other question's getting at. So we could bring this down here to 2b. If we look at what 2b is getting at, it actually is including the interaction in the model and allowing for there to be different kind of bendiness to those lines. So we'll go here to the visualize model and visualize this, and you'll notice now the way in which volatile acid explains alcohol, what? So think about this and the interaction. Ooh, look at that. Yeah, that's pretty interesting right there. The way in which alcohol explains the probability depends on volatile acid. So what wine would have the lowest probability of being low? Well, back here before 12.5 about, it's about 12.5, right down here. Before 12.5 alcohol, the one with the lowest probability would be small volatile acid wines. But look at the strong relationship on how quickly this changes right here, where above 12.5 or so, the ones with the lowest probability would be volatile acid large. So when is it better for wines to have high contents of alcohol? Well, that might be most important to the volatile acid large. Changes right around exactly. And so you notice it's not a consistent relationship in how it predicts probability. The strongest relationship with alcohol and probability of quality is going to be for the wines with the large volatile acid. They have the most steepedness line right here and has the strongest curve. This is going to be your reference kind of sigmoidal curve. This will have a negative coefficient for the interaction. This will have a positive. So when you look at the summary, we'll see a less steep sigmoidal curve. It's still positive though. So there's going to be a positive coefficient for alcohol and a negative coefficient for volatile acid small alcohol, and a positive because this one's more steep for volatile acid large, for alcohol volatile acid large. And let's take a look at the summary right here and see those coefficients we were just talking about. So it's important to kind of think through the coefficients of what you'll be getting. You remember how we said, oh, because it's two quantitatives. Yes. So yes, that's why my brain wasn't working properly. Volatile acid, these are two quantitative variables, but it shows you the implicit lines for values that are small, medium, and large. Brain was not totally working right there. But notice right here that as we go from, and let's look, small to large, so as you go from small to large, the curve gets more steep, and it's actually decreasing the probability. My brain is just going too fast today. So if you notice, it's getting a lot more downward sloped, and that is because we have the negative interaction. There is actually no alcohol of quantity 0 or volatile acid quantity 0. If there was, we would see a line that was actually positive. But it goes to like the 5th, the 10th percentile, the 10th percentile, the 50th, and the 90th when making predictions. Let's see what the questions ask. Among wines with the same alcohol content, which has the larger probability of being low quality? Now, because there's an interaction, it's asking which has the higher probability of being low quality. So when you look at this, is it the ones with small volatile acids, or is it ones with large, or does it depend? Which one has the higher probability of being low quality? So which one has the higher probability of being low quality? It would really what? Which one has the higher probability of being low quality? It would definitely, well, it would depend. Does that make sense, Kyle, right there? So because of the interaction, it depends. So you can't say it's always, like right here, you see how the red line is higher, but down here the red line is lower, and those are lines with volatile acid large. So over here, before alcohol 12.5, you could say that it depends, large until 12.5, and then after 12.5, about, I would probably say about, after about 12.5, then it's going to be over here with small. So it really depends, like, wait a minute, we would need to know the volatile acid to tell you. So this is the interaction right here saying, well, it's not consistent. And compare this to the previous graphic we had, where in the previous graphic, they all had the same. So over here, which wine would have the highest probability, and this is the previous question, which wine has the highest probability of being low quality? Is it small, medium, or large volatile acid? Which wine has the highest probability of being low quality? Is it small, medium, or large? So which wine would it be? Would it be has the highest probability at all points? Or does it depend here? And for this one, there's no interaction. So since there's no interaction, they all have the same, they're all parallel to each other. They're parallel S's. And so at all points, even if you can't tell it over here, at all points, volatile acid large has the higher. If you were to drop a line right here, the volatile acid large would have the highest, and it's always going to be higher. Does that make sense, Kyle, right there, to see that volatile acid large always has the highest probability? The other ones are always lower than the red line, and this is because there's no interaction. But in the previous graphic, there was an interaction. So which one has the highest probability? Well, it depends on what we see right here for the alcohol. Because volatile acid is not consistently one higher than the other. It depends on the level of alcohol. So that's some really good work there. At the top, yeah, it's hard to see at the top, but trust me, I guess trust me on this. They are parallel, and thus it'll always be the red line higher. They're basically like perfectly parallel S's, and then the red line's always higher, and the red line will always be higher here. So it's always going to be like on top of these because they're parallel. Like this is going to come down and go underneath it. And if you were to zoom in on this region, you would see that the red line is higher. But no, good questions. Well, that's got some good work there on the 2Bs. And so we'll head back here to the main screen. Let's do it. Ask more questions if you got them. That's a good start to the question. A lot of the work done right. Oh, that's like the end of the problem. I might have just done like 15-20% of the assignment. We got the models built, did a little interpretation. You're welcome, Kyle. Does that help out? Kyle, 100 points right there. Thank you for hanging out, doing some work, talking through those models, seeing how to make the output. We are going to get some 201. I really wish we had pizza tonight, but I shouldn't eat pizza every night, and we don't have pizza. I've started making garlic butter sauce for my pizza. I'm going to regret that. I should start working out again. Start working out May 5th last year. Got in shape. November, stopped working out. So I should be like, you know what? I'm going to do it again. I'm going to start working out. Come back to Knoxville in shape. I think sometimes it's interesting. Like people are like, Brian, you work out. You're in shape. You're fine. But I used to run a lot more. 29th, conference rolls. Used to run a lot. Again, visualization 7. Just run 100 miles a week. You say 100? Yes. I like pizza too. I love pizza. Pizza in the morning, pizza in the evening. When pizza's on a bagel, you can have pizza anytime. Let's check out some Viz 7 right here. And Priya, I think we got, which question you wanted the homework? We'll do that one next. We're doing a little Viz 7. We'll try to do a good bit of it. And we'll talk through it. Let me get some jump data up we can use. Homework 15 question. Which one, Alex? Ask away. Yeah. Let me get the timestamp right here on Viz 7. Viz 7. 5912 Viz 7. Here we go. Let's do it. So here we are with some confidence intervals inside of jump. Now this makes our life super easy. Yeah, I think we did that one in office hours earlier. So if we don't get to it, Alex, let me know. We got about 25 minutes left. Check out morning office hours. I'll send you the timestamp if need be. We did during morning office hours, so we'll check out time. Okay, so we have here a data set we need. We're going to go ahead and check this out in jump right here. Whoops, didn't click the right button. Oh, not class over. It's not class over. I'm probably going to use a different data set. Here's the data set you'll be using. Let me get a different data set open. Where's the data set for me to use? Let me get a data set. Data set. Where's my data set? Okay, let's go to the diamond data set. Diamonds. Oh, is that the one you're asking? Yeah, I guess we could do that right here. Priya's wondering about that one. So we got 2 people here wondering about that one. We got it. Let's do it. That was Priya's question. Okay, we got this. Let's take a look. You can't see it right now. This is not the data set you'll be using, so that's why we do different data sets right here. Confidence interval for a proportion. So No, you got it, Alex. We're going to do it here because Priya and you both want it. So that's a good time right there. You're both here. So we got this. Priya was asking about it. We're going to check it out, I think. So for the exercise, assume that the population of students is 5,374. We are going to take a random sample size of 400 something. So let's pretend this is diamonds that Tool 1 students are buying. Table subset. Pause right here so people can see. Table subset. With table subset, we are going to take a random sample size of 400 plus the last two of our UTID. Make sure to enter in your UTID. Click OK, and then we have our random subset. So 400 plus the last two of your UTID, and you'll create a random subset right here. I'm using a very different data set than you. Just make sure to use your data set and kind of go through these examples right here as we talk through them. So with this, creating 90% confidence interval, I do want to say this. Please look at the rubric. And if you are not graded by the rubric, please tell us. This is how you will be graded. And so check out these points as we do them right here. Let's take a look. Creating 90% confidence interval for whether or not someone has broken a bone. Now, this is a proportion of the people who have broken a bone. Using the yes as the desired response, take a screenshot of the bar chart, the frequencies of confidence intervals, and insert them into your Word document. So to create a confidence interval for the true proportion, we need to go here and let's make a confidence interval for, let's figure out the proportion of diamonds that are ideal. So I want to figure out the proportion of diamonds that are ideal. Why am I doing this? Because cut is a what variable. And look over here, because I'm doing proportions. And when you do proportions, it's because your variable is what? So cut is a what variable. So I'm able to do a similar type thing to this question because cut is a what variable. I can do proportions with it, and I can find out, I can estimate it's categorical. So we want to estimate, great job right there, Priya. It's categorical, which means we're doing proportions, which is also going to help us on the conditions here in a moment. We go to Analyze and Distribution. I'll pause right here on the screen so you can make sure to click Analyze Distribution for your variable. And when we go to Analyze Distribution, we're going to double click the variable of interest. Notice how it's red, meaning categorical. Now you'll notice you just have one variable right here. Excellent. When you do this, you will get a bar chart. We're going to click the top red arrow and click Stack. Pause right here. With the top red arrow stacked click, it's just going to put it in horizontal layout. Now I suggest, I'm trying to remember if the question says, I like to increase it to make it look nice and pretty right here. And then I do like to also go over here to histogram options and count access to include it. We haven't done project 2 yet. We might not have time today. We definitely do it tomorrow. But Connor, thank you. We'll see. Thank you, Connor. 100 points. There we go. Count axis. You can change the color of your histogram. All these nice things right here. Histogram color. Nice and purple histogram right there. Good stuff. We got our histogram nice and pretty. We got the count axis. You don't have to change the color, but looks nice and neat now. But now here's the real thing. Now we need to estimate the true proportion of diamonds that are ideal. So we want to estimate the true proportion that are ideal. To do this, we go to the red arrow and we go to confidence interval and then go to 90%. Now, if you needed something else, you could go to other and enter in whatever you needed. We need 90%. Make sure to enter in 0.90, not 90. And once you click OK right here, you will get your 90% confidence intervals in this case. We're only really interested in the ideal, which is right here, and how would this be interpreted? Probably the most important thing, when we were to the outcome, press the red arrow by cut and then click. Yeah, you can click. I think horizontal layout does it too. Great job, Priya, right there, 100 points. I usually like to do stack. It just kind of does it. Horizontal layout is, I think, okay too. It might keep the numbers below it. I like everything to be across. Preference, if you think the graders are mean, just let me know. But I prefer this right here. Want to grab this, take out picture, and bring it over here to Microsoft Word. Now, the important thing to know when you're doing confidence intervals is there's 4 parts to interpreting confidence intervals. I am blank % confident that the true blank is, and we gotta, can't do it like that. We gotta do it like this. There we go. That's much better. Is contained in the interval blank to blank. I am blank % confident. Now, the easy part is the confidence level. That's easy. I am, and you just grab the confidence level. So let's kind of highlight things right here as we do this. We'll highlight it in the output. I am blank % confident. Well, we just put the confidence level. We'll grab from our actual interval we're using. I am. And make sure to don't do it as a decimal. You turn it back to a %. I am 90% confident. Usually people get stuck on the next part though, which is I put a big blank for. So with this, and great job here right there, Do you know the next part, which is usually where people make the error? The true what? Remember, this is categorical. So we're analyzing proportions. So try to make it make sense. Like, you could say percent probably. I think I would probably say proportions. I would give points back if my graders took off for saying percent. But what are we trying to analyze right here? And then the interval, I'll highlight the interval right here. But with the interval is the lower to the upper. So I am 90% confident that the what? That the true what? So this is how we do the interpretations every time. It's usually on that big second blank where people get stuck, where they have to say, I am 90% confident that the true, and then I see like, ooh, I'm like, remember it's categorical. So what would it be? This is where the people usually are like, oh, I have no idea what to write for that second part. Well, what are you trying to investigate? This is the parameter of interest you want to understand. Yeah, Priya, 500 points. The true proportion of diamonds that are ideal is contained in the interval blank to blank. I'm like, you're just trying to figure out what proportion of diamonds are the ideal. Great job, and Jessica, great to see you. So I am 90% confident the true proportion of diamonds that are ideal is contained in the interval, and then you just give the interval. There it is right there. I am 90% confident the true proportion of diamonds that are ideal cut is contained in the interval 36.36 or 63 to 44 point, and that's it. Now, what's so great about this, and we'll do maybe conditions. I think it asks you to check the conditions, but what's so great about this is if you do this for a quantitative y, which it asks you to do for the second one, we'll do a little extra here in a moment, but now it wants you to do it for a quantitative. And this is when you're trying to figure out the true mean. I think it even says, it probably says true mean here somewhere. But does it not say about the true mean? We do conditions here in a moment. This is proportions. There it is. Yeah, confidence interval for the mean, confidence interval for the proportion. I was like, where is it? So this is a confidence interval to estimate the true proportion. This is a confidence interval to estimate the true mean. And this one is quantitative then. I said categorical. This one's quantitative. So now we'd have to go back over here and do the same sort of work, but do it for a quantitative variable. Does that make sense, Priya? So now we're going over here and doing the analyzed distribution, same thing we did a moment ago, and we're doing it for your other variable right now. And we're going to go right here and take a quantitative variable for an example and grab this. So we're going to grab the carats and diamond, and there we go. We're going to go to the top right arrow and go to stack like we just did previously, same sort of steps. And now that we have it stacked, we can make this a little bit bigger and be like, okay, I like my graphics a little bit like that. Don't have to. Just like look nice and neat. Christopher, great to see you. And then we're going to go right here, go to histogram options, count axis. There's our count axis. We're going to click and make it nice and neat color. Go down here, a little blue today. There we go. And now we go here and it's at 97.5. So we got to go to the red arrow, and these are the things that are required, and go to confidence interval. And now we do have to go to other. This is going to allow us to enter in the percent confidence we want when making the interval. So let's go ahead and click other right here. And then we can choose, we choose the two-sided. You don't know sigma, that'll do a Z interval instead of a T. Let's click OK right here. And now we have the 97.5% confidence intervals. With this output right here, I might include it as separate screenshots. Probably I'd go right here and I'd take my screenshot of this. There we go right there, nice and neat screenshot. And I'd go down here, and then I'm going to put this here because what we just did can help us answer the previous question. So I would include all that output right there. There we go. And go back over to our output. There's our screenshots. Good stuff. And make this a little bit smaller. It can be a little larger, but not too large. That's great. Perfect. That's a great idea. There we go. So we are trying to talk about the carats of a diamond. So we're saying like what the truth is for like diamonds people buy, the true mean carats of diamonds. So Priya, how would this look? And this is really good practice for the test. If you get to the test, the true mean amount of the carats. Yeah, exactly. Great. That's worth another 500 right there. That's perfect practice for the test. So if you put it to a full, I think you're just doing the hard part, right? Which is, yeah, that's worth some 500 points right there. Great work. I am 97.5% confident that the true mean amount of the carats in the diamond's weight is contained in the interval. And then we go right here. So let me highlight the stuff in this output for what it's relative to. We're trying to figure out the true mean. and that is relative to this right there, the true mean carats in a diamond. So this is true mean of carats. Notice how we're trying to figure out the true mean of carats in a diamond is contained in the interval, and then you go lower to upper, and those are not percentages. I think that's where people can make an error because, you know, like a 1 carat diamond's pretty big. That's not a percent of carat. That's like the average carat weight, because I guess carats are in weight. I don't know how carats measured, but man, I just got some diamonds, but does that make sense? I didn't do the full thing because I thought oh yeah, no, that's great, Priya, that's excellent, that's good practice. The middle part's the hard part. I mean, I think usually people can find, if you notice I've got this color coded right here, to that is the percent confidence, which would go up there in that interpretation. And then the other one is the what are we talking about, which is the hard part for people. And then the interval is usually pretty easy too. But when you think about this, it's the middle part where the errors occur. Last but not least, I guess, with this is the conditions. We can go over them really quickly here, and then we'll try to get one more problem in. But when we do the conditions matter on the type of data we are using. And I will say this, the best way I like for people to write out conditions is to do the following. When you're doing your conditions, we go here and we always write our conditions like this. You might want to go here and do random, and then say something like it is met, and then give reasoning. Probably going to see everyone using this format now, which is okay. And you could even go right here and do a numbering on it. Condition 2 is 10%. You can talk about, is it met? Now, it might not be met. It is, I'm not saying it's not met, but maybe it's not. And you could give the reasoning. So I guess you could, is that looking odd? I don't know. You can use whatever format you want, but kind of making it clear. That might be the best way to do it. And what do I mean by reasoning? You need to talk about it. You need to explain why. Now, wait, Priya, what do we do before we get to condition 3? Before we get to condition 3, what do we do? It's met. I'm just pretending. It's met. We pause before we get, if it was not met, you might want to say it's not met. We pause in the chat, we pause and we ask what kind of data. So we pause and we say, well, what kind of data are we working with? Because condition 3 is data dependent. If we have here categorical data, it's going to be success failure. So we'll copy paste this for a moment. Success failure, which is we need at least 10 successes in our sample, at least 10 failures. And then the nearly normal, can I make this go down a number? I've always wondered how to make this go down one number. Oh my gosh. I think I did it. Now there's not the condition 3. We can definitely go over this during other office hours, probably, because we're going to try to do another question. Look at that. Perfect. Condition 3 is dependent on the type of data you're working with, where if you have categorical data, you're doing success failure. If you have quantitative data, you're doing nearly normal. So definitely review these conditions where success failure is we need at least 10 successes, at least 10 failures, and nearly normal can be met 4 ways. 1, does a histogram look normal? 2, does the normal probability plot follow a straight line? 3, does the goodness of fit test have a p-value above 0.05? And 4, do we meet the large enough n condition, which is now part of the nearly normal? But we're going to try to, so Priya, we might speed run a question here because we've got 19 minutes till class. I'm going to send out an announcement here, Priya, but is it the organization monitors question on chapter 3 or chapter 15, question 3 homework? We might try to speed run it here. How's that sound? We'll do a speed run. We'll head over here to the main screen. So let's try to get a speed run. And I'm going to send the announcement to class about it coming up. It's the organization monitors. Let's check it out. Organization monitors. We're going to speed run some questions. But how's your day going, Priya? We've got a lot of work done. 19 minutes till class. I'll say 20 minutes to them. 20 minutes till class. See you soon. Click here. There we go. Got it sent. Ready to go. Okay. Forgot about that earlier. Pretty good. It's been a good day. It's I'm really tired today. I got like 8 hours of sleep last night, but I don't know. I'm just pretty beat. I'm still recovering from the weekend. I was busy. Didn't have that crazy of a weekend, but I mean, get married. It's busy. Okay. So many things. Fun times. Okay. Organization monitors. Trying to like organization monitors. Chapter 15, homework 3. Organization monitors. We're gonna do a little speed run of it here. So I'm gonna mention the problem. I'm gonna grab some food too. We didn't do TV ads today. Okay, so let's head over here. Check it out. Okay, everybody, this is the organization monitors problem. And with this, we did a version of it earlier today where we spent 22 minutes on it. So check out the morning office hours where you can see the long play of it. We're doing the speed run today. Where we did a 22-minute solve of it. So we're going to show that we can solve it a little bit faster right here. But in the morning office hours, we did it step by step. Step 1, write out the null alternatives. Step 2, find the z, the t, the chi-squared. One of those, we have to find the test statistic. Step 3, find the p-value. And step 4, reject or fail to reject. And we went through and kind of lecture taught it. So if you want a more thorough how to understand to do it, that's how to do it. This one's going to be a little bit quicker because I'm going to be teaching her soon. So if this goes a little quick, check out the morning office hours where I'm a lot slower on solving it. So get ready here. Here we go. The null Priya always has the what sign. Whenever we write out a null hypothesis, it always has the what sign. The null always has the what sign. I will find the z here in a moment. The null has the equal sign. Now you'll notice that they are wondering if the figure has changed. So if they are wondering if the figure has changed, what should the sign be for the alternative? They are wondering if it's changed. They said, do these give evidence, the alternative-based claim of a change? Great job, Priya. Excellent work. The not equals. And that's because the question itself dictates what we're doing. Priya, I just want to throw you 1,000 points. Priya, thank you so much. We're going to do a great job. And let me know, Priya, if I need to slow down. We got enough time. Don't worry. I know I'm speed running it, but tell me if I need to slow down because I think you're on the z-score, which the conditions right here. Is it random independent? Probably. Is it less than 10%? Probably. Is success failure condition met? This is met because 34% of this, which is the percent, this is the p hat right here. Notation Leo is going to tell us. That's p hat, that's p naught, and that's going to be n right there, which is going to come into play here for the z-score in a moment. Now to find the z-score, we need to take the question. So I'm going to take a screenshot of the question, and we're going to solve it here on the screen. Okay. So to solve for the z-score, we need to go here and do p hat minus p naught over p naught q naught over n square root, and that's the z-score. So p naught is going to be the hypothesized truth. Notice that this is also what we see in the null hypothesis. So we know that that is 0.35. And then we see right here that p hat is given to us in this instant. We don't have to solve with x over n in this instance, but that is p hat, which is 0.34. The bottom of this equation is the standard deviation. I clicked the music button. This is the standard deviation because it's based on the truth, not called a standard error. What it's called is not so important. The important thing is this what we're standardizing by. If you're wondering how I got 65, that's because it's 1 minus 0.35. Remember, p naught and q naught are complements of each other. The sample size has not been circled yet, but that's the sample size of how many students they spoke to, so it goes right here. And now solving this, we'll go to the calculator. This will solve out for the z-score. So the top is negative 0.01, 0.35 times 0.65. Nice job, Priya. Thank you so much. And we'll square root this, and there we go. And that's over. There we go. That's got it. And we can kind of guess the p-value on this because this z-score right here, we're going to take and copy it. When it comes down to the next question, the next question is going to ask us the p-value on this. And for the p-value, let's think about what we have here visually. Well, we landed at 1, almost 2 standard deviations below. But the question says we are testing to see if there's a change. A change means we're using the not equals alternative, which shades to the left and the right. So we need to do a reflection on the other side of the curve on the same side. So if you look at this, and that's not the best drawing I've ever made, it should be a symmetric reflection. There it is right there, and that's where the z-score is at. If you're wondering where I'm putting this line, it's at the z-score of negative 1.914. And going back here, we can look at the David M. Lane. So remember that little horrible drawing I did right there? But this is going to be where we get the answer from the David M. Lane. Now, it's probably going to be about, my brain's thinking, it's going to be about 0.068. No, it falls a factor. 0.064. No, what did I write with my 0.068? I'm taking guesses. No, we were close. Okay, let's go find out the actual answer. We'll be close. It's probably 0.059. So let's go outside of this. Oh, I lost it from my copy paste. So there's the outside of this, and remember our picture we drew a moment ago. There's the actual drawing of it, and here's our drawing of it. So we'll put them both on the screen so you can see them. There's my little horrible sketch of it, and there's the actual sketch of it where we're actually looking at it. Can't get it on the screen at the same time, apparently. But there's my sketch of it, and there's the real version of it. So you can see what it should look like. And so this is the area 5.6%. So if we go back and put in the real numbers, I was kind of close, but not good enough today. So that would be it right there, rounded properly, and that's got it. So make sure to put it into the applet. On the test, we could show you pictures. We could have you kind of make guesses, but knowing how to use the applet is important. Now, the last thing we need to know right here is when the p-value is low, what the null. We only do 2 things here. We either reject or do not reject, also known as failed reject. But when the p-value is low, what the null? When the p-value is low, what the null? And the p-value is lower than alpha. So the p-value is lower than alpha. And if the p-value is lower than alpha, you are going to what the null? When the p-value is low, p hat, p naught, and p. P hat is from a sample. P naught is hypothesized, and p is the truth. And practice on what the question says. Like it says, like we assume, that means p naught. It says, now these questions you will not know the truth, so you'll never know p because we're just kind of making guesses of what the truth might be. If you ever see a sample size, that means it's a p hat. Does that make sense, Priya? Anytime it's associated with a sample size, i.e. n, then it's going to be p hat. Anytime it says like assume or they want to test against this, that's a p naught. So things that are assumed or tested against would be p naught. Things that come from a sample are p hat. And for these types of problems, we would never know the truth. So that's always going to be what's tested, like p equals p naught. Because we don't know the truth. We're just saying, do we think the truth could be this? Which is what we assume according to the null, that p is p naught. Does that make sense, Priya? So the wording of the question will distinguish whether it's something we assume, whether it's something we got from a sample, or whether it's something we know is the truth, which we won't have for these problems. We won't know the truth for these problems. Since the p-value right here, and this is not a p as in proportion, this is a probability of our results or results more extreme. Since the p-value is below the alpha level, when p is below alpha, we reject the null, and that means there is evidence for the alternative, and that would mean it has changed. There's evidence it has changed. Yeah, the keywords would be like, we assume it's true. So let's look at that right here. So they're using this as the baseline number right here. So that's what is assumed true. And then it says in 1999, a sample of this size gave a number of this. So this number right here is associated with the sample size. This is the number we're testing. They're trying to see, has it changed from this number? So that's the tested value. That's the p naught. Now, we don't know what p is. We're just saying that this is the truth. Yeah, no, this is good questions right there, Pira. And then this difference is probably not meaningful because it's a very small difference. This is only 1%. And what do I mean by that? The figure dropped from 35 to 34. So is it really that significant of a change? Nah, not really. It went from 35 to 34. So although it's statistically significant, it probably doesn't have any practical or meaningful real difference. Great job, Priya. Excellent work. Swing by more. We'll be doing more work. And this is a good question. Lots of great practice. We did much longer solves on it earlier today. And I do want to point out the ways in which we were solving these. I think this is the exact same one right here. We went through and highlighted everything. So if you want to see a more comprehensive solve and follow through the steps of write the null alternative, find the z, the t, the chi-squared, find the p-value, reject or fail to reject, follow through the earlier portion of the video where I walk through and I color code everything and show you how to find each step and what it means, especially with doing the tests. But great work, good practice, and we'll be back here later. Keep up the great work. Bye for everyone. Bye. I'm going to go eat some peppermint patty bunnies. We got those from Easter still. Bye, everyone. That's a healthy lunch.